Hello all, good morning. This is Dr. S. Subalakshmi, Assistant Professor in the Department of Mathematics, SNS College of Technology. Today we are going to see a case study video on multiple integrals. In the previous classes we have seen problems on multiple integrals and the design thinking approach on multiple integrals. But now we are going to see the case study on multiple integrals. So we have two more problems to discuss with.
Content and purpose. This case of study presents two independent applied problems using a multiple integrals. A, computing the volume of solid bounded out by a parabolic and a plane. B, computing the probability over a triangular region for given joint PDF. Each problem given with a short real world motivation, a precise mathematical statement and a step-by-step solution. Interpretation of results, checks and brief extension ideas you can use in the class or assignment.
So this is the context and purpose of the study wherein we have two problems. One is volume of a solid and another one is probability over a field. And each problem has been precisely explained using the mathematical statement, the real world motivation and also the results and checks have also been given. This is what a short note of the case study.
Volume of a paraboloid, engineering or design application. Motivation, estimating storage volume of a basin or an open tank whose top surface is shaped by a paraboloid. It's a routine engineering task. Examples, reservoirs, cooling ponds. Accurate volume calculation informs materials estimates, capacity planning and safety margins.
So here is our problem statement. What will be the problem statement according to the motivation given here? You have to find the volume of a solid above, rounded above the curve, which is z is equal to 4 minus x square minus y square. This is a mathematical equation. And below the plane, which is the plane, z is equal to 0.
Identify projection region D in the xy plane where z is greater than or equal to 0, that is 4 minus x square minus y square is greater than or equal to 0, which implies x square plus y square is less than or equal to 4. So D is the disk of radius 2 centered at the origin.
So here what we have explained is on projecting this particular region in the xy plane, we have got this equation as x square plus y square is less than or equal to 4, which means it is a disk of radius 2. It is a disk of radius 2. And we can express it in the volume as this particular double integral. Volume is equal to double integral over D 4 minus x square minus y square into dA. dA is the area to be integrated.
Switch to polar coordinates. X is equal to r cos theta and y is equal to r sin theta dA. R dr d theta, then the integrand 4 minus x square minus y square equal to 4 minus r square. Limits r belongs to 0, 2. Theta belongs to 0, 2 pi.
So what we have done here is we have used the polar coordinates to expand this particular integral because we doesn't know formula or the theoretical expansion for the volume of the integral previously. But here we can use the polar coordinates where x is equal to r cos theta and y is equal to r sin theta, and we will have this dA to be implemented by r, and r's limit will be 0 to 2 and theta's limit will be 0 to 2 pi. Therefore we will be setting up the integral by interchanging the variable a from theta. R theta. Okay, so b is equal to integral 0 to 2 pi and integral 0 to 2, which we have double integral 4 minus r square into r into dr d theta. And also we are going to integrate it carefully using simplified methods of integration. So this is what we will infer.
Value to be 4.
So when evaluating at r is equal to 2, which means the disk is of the radius at center 2 with radius 2, therefore we have the value is 4. Now
compute the angular integral.
Now we are going to compute the angular integral here. What do you mean by the angular integral? It is of single integral type, wherein the limit is 0 to 2 pi and 4 into d theta. Only the angles have been chosen here and evaluated. So the value will be?
Final answer is equal to 8 pi cubic meter.
So the final answer will be the volume of the whole of the volume of a solid using the paraboloid and the z plane is 8 pi cubic meters. This is what a case study. We have implemented multiple integrals in our volume study.
Probability over a triangular region, statistics, probability application, motivation, joint probability density function depends on a region, arrives in modeling correlated continuous variable, calculating probabilities over sub-region events in frequency tasks, in reliability, signal processing and spatial statistics.
So this is a task wherein the probabilities over the sub-regions is very frequent task for the engineers, wherein the reliability, signal processing and the spatial statistics have been analyzed.
Statement. Let the joint PDF over the unit square 0,1 into 0,1 be f of x, y equal to k of x plus y for 0.
So there we have got a joint probability density function. No, this is what the joint probability density function of the given function with given area. So f of x comma y is equal to k into x plus y for where x lies between 0 and 1 and y lies between 0 and 1. This is your probability density function, and later we have to determine
k, compute p of x plus y less than or equal to 1.
So we are about to determine this k value constant, and we are also about to compute this probability of x plus y less than or equal to 1. So that we will have the volume, which means the area of the double integral.
Solution. Find normalization constant k.
So we are going to find the normalizing constant k as discussed in the previous slide. So using the normalizing condition, which is the normalizing condition here, wherein the double integral follows here, where 0, 1 the whole square represents the limit lies from 0 to 1 for both of the integrals. So its value is equal to 1. Now to evaluate the integral without k, we have to use the normal methods of integration to compute.
Inner integral.
Integral 0 to 1 x plus y into dx. This is our inner integral. We are going to evaluate it. So its values will be
Half plus y.
1 by 2 plus 5. On just a mere simplification, we will have the value to be 1 by 2 plus 5.
Now integrated in y.
So integrating in y, which means we are just taking the integral part of y alone and we are integrating. So its value will be
1.
1.
Therefore,
your k's value is 1. So therefore the normalizing constant's value is 1. And so this f of x plus y becomes x plus y alone. F of x comma y becomes joint density function becomes x plus y alone.
Compute p of x plus y less than or equal to 1. The even x plus y less than or equal to corresponding to the triangle region E is equal to set of x plus y is equal to.
This is a circular form of the triangular region here, which is inside the unit square. So we are going to set up the integral with the help of the circular form here. Therefore, p of x plus y is less than or equal to 1. The double integral over t x plus y into dx dy. Using this only we are taking this particular double integral. And therefore its value y belongs to y ranges from 0 to 1 and x ranges from 0 to 1 minus y and x plus y into dx dy as usually. Now you are going to compute the inner integral, which means the inner integral alone for which corresponds to x alone, and the value will be 1 by 2 into 1 minus y the whole square plus y into 1 minus y.
Simplifying stepwise. We have 1 by 2, 1 minus 2y plus y square plus y minus y square will be equal to 1 by 2 minus y plus 1 by 2 y square plus y minus y square will be equal to 1 by 2 minus 1 by 2 y square. Integrating with respect to y, we have p will be equal to integration of 0 to 1 into 1 by 2 minus 1 by 2 y square into dy will be
We have
equal
just
to
taken that value here and integrating with respect to the variable y. Therefore, we will be simplifying it with the limit 0 to 1 and the simplified value is 1 by 3. What will be the final answer then?
p into x plus y less than or equal to 1 will be equal to 1 by 3.
So the probability of x plus y less than or equal to 1 is equal to 1 by 3. Now we have computed two of our case study values here. One is volume of a paraboloid and the other is volume of a using double integral. We found the area of a solid. So this is how we case study multiple integrals and we implement this multiple integral in our real time applications. Thank you.